So welcome everybody to the third part of today's lecture about wireless security, continuing with what we have been discussing and talking about from where we left off. We talked about the weaknesses and the drawbacks of the current encryption methods, especially the RSA and ECC, and how they are prone to Shor's algorithm and quantum computers. And we talked about potential solutions to the above problem, including lattice-based cryptography, hash-based, light cryptography, advanced encryption, quantum cryptography, and physical layer security. And we mentioned that one of the most promising solution is physical layer security because of the reasons that I just mentioned before, including the unnecessary need for having shared keys or trusted node parties to share keys between the nodes, or using complex mathematical functions to make it difficult for the hackers to attack, and the possibility of achieving the security level of one-tap pad encryption method described by Shannon back in his paper 1949. So now, what's physical layer security? We will talk deeply about it in this course, but for now I will just quickly introduce you to this domain called physical layer security. So we start with the current communication system and the standard. Most of them are generally designed without considering physical layer security, assuming that secrecy can be provided and achieved using encryption, decryption at the upper layers, as we explained before in the previous slides. However, there are many issues with cryptography. In addition to the ones that I mentioned, there is the issue of key distribution. It's very difficult, very challenging. You need to have a trusted third-party node that's authenticated and everybody trusts it, and this is responsible for sharing the keys. When you share the keys, you need to share them securely. And how are you going to share them securely? Over unsecure channel. In addition, the second problem, perfect secrecy, is hard to achieve. It's impossible almost. Public cryptography is, nobody can prove in math that asymmetric cryptography can achieve perfect secrecy. Just symmetric cryptography can achieve perfect secrecy when under the condition when you have a key length of the same length as the message length. Let's say you have 10 gigabit of data and you want to send them, you need to have a key length of 10 gigabit, not 284 bits, not 2048 bits, not, you understand me? Just the ones I showed you in the website before in the first part of this lecture, where I showed you the public key length, and it's around, for RSA it's around 2048, and for ECC it's around 256. So I showed you that this is the key length used to secure your communication. What does this mean? This means that each time you want to send new data, you are generating a new data, let's say new message, new voice, new video, whatever. Each time you want to send this new data, you are again using the same key over and over and over. And this makes the method not so secure, because hacker can just start analyzing this traffic. If, for example, with different data, you are using something static. So he can analyze this, and in the long run, he can find some patterns in this, and he will be able to know the key. And he will need, somehow he might be able to crack into the method and get the data back. So this is really difficult, perfect secrecy. Perfect secrecy means that no matter what supercomputer you will use, no matter how many antennas and the SNR level you will get, regardless of all these things, you have no capability whatsoever to crack the security algorithm. So imagine the amount, how strong this method is if you can achieve it with physical layer security. So, which means that the length of the key that you will use is the same. If you were to translate it to key, the length of the key is the same as the length of the message itself. And whenever you have a new data you want to send, a new key will be regenerated. And this key, the amazing thing about this key, is not shareable. Means you don't need to let the other party know about it. This is coming from nature, from wireless channel, from the properties of the wireless, exploiting this feature of wireless, the beauty of wireless, to make sure that nobody can hack this method. So the current encryption algorithm, we already discussed that they can be hacked and they cause complexity, delay, signaling overhead, throughput reduction, power consumption, too much power consumption. Therefore, physical layer security is one of the key concepts and powerful alternatives that can complement and may even replace. Now, I said here may complement. I said can complement and may even replace. Some people claim that physical layer security alone we cannot depend on physical layer security alone to secure our systems, but we can use it as an additional layer, an additional security layer that can improve our communication security, which means that you are adding additional overhead, additional delay, additional processing, additional power consumption, additional complexity, and not using it alone. You are using it with the previous other encryption methods just to make it harder for the attacker to get your message back. Personally, I'm against this approach because it doesn't solve the existing problems of reducing complexity, reducing delay, latency, making our system less complex, especially with the current emerging massive machine type communication and Internet of Things devices. We need lighter things. We need something that's light but extremely powerful in terms of security. So I am a strong advocate of the capability of physical layer security to replace encryption-based approaches. Strongly standing behind this line, although up till now no physical layer security company exists in the world, although I know some companies are working on this, but up until now there is most of the people are still working on the application layer. And the reason for that, security domain was perceived among people as an IT domain or computer engineering domain. Nobody thought that security domain is basically an electronic engineering problem, and most importantly, it's a communication problem. The communication guys, the communication experts, the communication people should consider their transmission to include inherent security features while they are transmitting their data. It shouldn't come up as an add-on. It shouldn't come up as a patch that just adds more redundancy, more complexity, more overhead, more things that you add to your system, which you can really get rid of them by just properly redesigning your modulation scheme to consider security and take it into account while you are designing your system. So such a powerful thing, this triggers into your mind that things should be redesigned again from the bottom up, while considering that security is basically a communication problem. It's not only an IT problem or a computer engineering problem who solve this problem by their own approaches and their own perspective. We should get into this field and claim this problem and take full responsibility and solve it once and forever using such approaches that we will teach you during this semester. So put 100 lines under may even replace encryption-based approaches. We are strongly behind this claim, this statement, and we will prove it by mathematical derivation, and we will prove it by practical simulations and practical implementation of physical layer security techniques that can achieve these unbelievable targets. So what's physical layer security then? If it can do all these things for us, what's it then? What's the basic idea and basic concept of physical layer security? So for those who are familiar with wireless, they know that the medium between you and your between the transmitter and receiver, there is a wireless medium, yes? The wireless medium is, think of the wireless medium is your fingerprint that changes based on the location of the device. For example, we cannot find two people who have the same fingerprint in the world. Is that right? That's right. So the fingerprint can be treated as a key, can be treated as a private key or something that's unique to you. Your computer can open only with your thumb, with your fingerprint. Okay, no two people on Earth have the same DNA structure. True, although 99.9999% they are the same, but there is slight percentage they are different, and due to this, we say that they are unique. They are not the same. The same thing applies to wireless domain, to wireless science, to wireless medium, to wireless communication. If you are standing in point X and you are receiving your signal from a base station, and you move to point Y, and the distance between X and Y is, let's say, 8 centimeters. What's the length of your? Usually, any slight movement with your device will be in centimeters. Yes, nobody can come exactly just on top of you and put his device on top of your device to play or use his device. Or if he wants to hack you, nobody can just come exactly on the exact physical location of the user. If he wants to hack you, you cannot allow him. You will push him. And this unique feature, since the wireless signal changes based on the exact location of the user, then the response of the channel with respect to each user acts as a fingerprint. Okay, as a fingerprint, unique feature that cannot be replicated, and it's different from all the other responses, wireless signal responses that are caused at different locations. So we call this feature the spatial decorrelation, the spatial decorrelation property of wireless signals. So the signal will change dramatically based on the location of the device or of the user. Now, since it can change based on the location due to the reflection, diffraction, and many other properties of wireless medium transmission, then each one in a certain location has its unique fingerprint, that unique response that he can utilize as something that's only known to him and the transmitter, the one that sends that signal to him. So this is the first property. The first property is spatial decorrelation that we exploit in physical layer security. The other property we exploit is reciprocity of the channel. Reciprocity means that the channel response from the downlink, from the transmitter to the receiver in a TDD system, time division duplex system, is going to be the same as almost the response of the channel from the receiver to the transmitter. For example, when you are downloading your data, you experience downlink channel. The response of wireless medium in the downlink side is going to be almost the same as the one in the uplink. And this property, we call it the channel reciprocity, means the channel is reciprocal, the channel is similar in both directions. This can be achieved only when you have a TDD system, which means that you must use the same carrier frequency for uplink and downlink so that you can enjoy this property of wireless signals. Otherwise, the property will not hold. Those are two key properties. In addition, we have impairments in the wireless channel, such as noise, such as fading, such as interference, dispersion, and other phenomena like diversity. All these can be well designed together and can be intelligently and judiciously exploited in such a way that you can achieve perfect secure communication without the need for encryption whatsoever. So what does this mean? This means that you will come to the IT security world and tell them you don't need to use ECC, you don't need to use RSA, you don't need to use DSA, you don't need to use hash. Those things, you will tell them those are things of the past. Those are the old approaches used to secure wireless systems. Now, we are providing you something that can overcome the problems caused by these old approaches and even provide you with perfect secrecy that does not depend on the computational power capabilities of the hacker, that does not take any regard to the devices or tools or softwares that the hacker might have. So this is the key motivation and key intelligence and the driving force behind physical layer security. So we will be, in this course, we will be learning little by little how we are going to utilize these things to come up with novel algorithms that can achieve physical layer security. And we will give you examples, we'll share with you codes and give you practices and give you some tasks as well and some papers to read so that you can understand how these things are being implemented. So far, physical layer security is just in the research phase. It's not yet standardized. It's not used by any wireless system so far, and but it's expected to be something in the future. And we are preparing you for the future. That's why it's very critical, very important that we teach you this concept and all of its ins and outs. So all in all, the main design goal of physical layer security is to increase the performance difference in terms of signal to noise ratio, in terms of reliability performance, throughput performance between the link of the legitimate receiver with respect to the transmitter and the eavesdropper who tries to listen to your communication with respect to the transmitter by using well-designed transmission schemes. So this is what we are going to talk about and discuss and explain to you in this amazing, unique course that's given for the first time in even many universities. This course is not available in all the universities. Very few, even not everybody can teach this course. So here, this is a golden opportunity for you to embark on this field, and the end goal is to come up with an algorithm that can really prove its capabilities, and then hopefully you can use this algorithm, patent it, and propose it to some companies who will be interested in this. So with this, we can stop here and continue next lecture with the material related to the security in wireless networks and how they are addressing the requirements in Wi-Fi, LTE, 5G, and the other technologies. But special focus will be on physical air security after that. And this was just a brief introduction of what physical air security is, the advantages, the potential of it, and what we can do with it. So thank you everybody for being with me and for joining me on this exciting lecture. And I look forward to seeing you in the next coming lecture. Take care and stay blessed, everybody. Salam.
Thank
Thank you.
you.
Thank you.
Thanks a lot, Mr. Bashir.